Alright, this will be section 3.6, number 9. In order to get started on this problem, you're going to have to understand what the derivative of a logarithm will look like. So if you have the derivative of a logarithm with base b of x, you're going to get 1 over x times the natural log of the base. Now, there's a special case scenario in which you have the derivative with respect to x of the natural log of x, or this is also known as log base e of x. So we'll call it that for now. So when we throw this into this formula right here, your derivative is going to be 1 over x times natural log of e. But since the natural log of e is only equal to 1, that means that the derivative with respect to x of a natural log of x is equal to 1 over x. You've probably seen 1 over x as being the derivative of natural log of x. This is where it comes from. So whenever you have a base other than e, you're going to have to know this right here is what that's equal to. Now, sometimes what's inside of the parentheses for your logarithm, so say you have the natural log of x squared, such as this problem, this value inside the parentheses does not equal to x. So you're going to have to do the chain rule, which would give you something that looks more like this. The derivative with respect to x of a logarithm with base b with f of x, and by f of x, I just mean some sort of function. In this case, we're going to let it represent x squared. So f of x will be equal to x squared, right? So in this one, what you'll do is by the chain rule, you'll solve it just as a normal logarithm on the outside. So it'll be 1 over 1 over f of x times natural log of b. And now by the chain rule, you're going to derive the inside, so this will be times f prime of x. So if we did the problem that we have here for number 9, all you would have to do is say that the derivative with respect to x of log base e of x squared is equal to 1 over x squared times natural log of base e, which is equal to 1, times the derivative of f of x. So f prime of x is going to equal to 2x, since f of x is equal to x squared, so times 2x. This would simplify to equal 2x over x squared, or 2 over x. Now, another important portion of deriving, or anytime you work with logarithms, is that you cannot take the logarithm of a negative number or 0. It has to be a positive value inside of the logarithm. So that means that x squared must be greater than 0. Now, because x is always going to be positive, since x squared is always going to be positive, whether x is negative or positive, that means that x must be greater than 0. Because whether it's negative or positive, it's always going to end up greater than 0 once you square it, as long as x is not 0. So the value of the derivative will be 2 of x for all values from negative infinity up to 0, but not actually 0. Just this parentheses right here indicates that it does not actually include 0. It's non-inclusive. And 0 to positive infinity. This is your range on which this function will hold true, everywhere except 0. So x does not equal 0. That's how you're going to solve number 9. Okay, now natural log of x plus 1 over x minus 1. This is problem number 11 in section 3.6. Now this one can be solved with the same exact function as you have before. So we know that the derivative with respect to x of a logarithm with base b of f of x, in this case f of x, will be equal to x plus 1 over x minus 1, will be equal to 1 over f of x natural log of base b. In this scenario, since we have the natural logarithm, our base is e. So what I would like to do is just assume that whenever we're doing natural log derivatives, we can just ignore this portion of the formula. So it'll actually come to just be natural, or 1 over f of x times f prime of x whenever you're taking a logarithm with base e. So this is a little bit more simple of a function, and you're going to work with natural logs a lot more often than you're ever going to work with any other kind of log. So sometimes it's useful to just remember that it's 1 over f of x times the derivative of the inside of the function. Now in this scenario, that's going to actually equal to 1 over x plus 1 divided by x minus 1 times the derivative. So I'm going to find f prime of x over here on the side. Or actually, let's not do it there. So f prime of x, this is going to take up a lot of room. So f prime of x, so we'll just say that this is equal times f prime of x, and we'll fill that in later. And we'll just finish the rest of this board off with just doing f prime of x, because we're actually going to have to do the quotient rule. So u is equal to x plus 1, v is equal to x minus 1, u prime is equal to 1, v prime is equal to 1. So we know that it's f prime of x is equal to low d high u prime times 1, or minus high d low, so x plus 1 times 1, divided by v squared, x minus 1 squared. So you may want to just, from here, simplify a little bit. So x plus, so this, I'm just going to take this out, because it's just 1. It's irrelevant. It doesn't matter. It's like that R I told you about. So x minus 1 minus, we'll distribute that negative to make it easier to look at. So we got x minus 1 minus x minus 1, which is going to cancel out these x's, because that's x and negative x. So we got negative 1 minus 1. This top will cancel to negative 2. So f prime of x is equal to negative 2 over x minus 1 squared. Throw that in right here. Negative 2 over x minus 1 squared. Right? This is all equal to the derivative with respect to x of natural log of x plus 1 over x minus 1. So when we simplify this, right, so this is the same thing as multiplying by the reciprocal. So 1 divided by this is actually just equal to the inverse of this one. So we'll flip this one and put it on top. So that's x minus 1 on top. Now, if you look, this is all multiplied across, so you can distribute this negative 2 over here. Right? And this is multiplied across, so you can just draw this line like this. But now you have x minus 1 on the top, and you got x minus 1 on the bottom, so you can cancel that out. So this will go to 1, and this will go away. So you got negative 2 over x plus 1 times x minus 1, which is actually just equal to x squared minus 1 when you FOIL this out. Go ahead and do that on your own. So it's negative 2 over x squared minus 1. Now, this is your answer right here. But you have to remember the last step when dealing with logarithms, and that's finding where your function is defined. This one is going to be a little bit more tricky than usual, because we have to define everywhere, since it's inside of a logarithm and logarithms have to be greater than 0, everywhere where x plus 1 over x minus 1 is greater than 0. Now, if we just look at this and try and figure it out without any kind of algebra, you'll see that if you have a number that its absolute value is greater than 1, so say 2, you'd have 3 over 1. This would be a positive value. That's fine. If you had negative 2, you'd have negative 1 over negative 3, which is a positive value since you have a negative divided by a negative. That's also fine. So we know we're looking for some way to prove that if the value of x has an absolute value of greater than 1, that this will be positive, and that's what I'm going to do in this next step. So we'll put it over here. So x plus 1 over x minus 1 is greater than 0. Now, when I multiply this across, so if I multiply x minus 1 over here, depending on whether or not x minus 1 is a positive value or a negative value, you will have to flip this sign. So we'll make this into a piecewise function. So that'll be that x plus 1 is greater than 0, assuming that x minus 1 is greater than 0. And you'll say that x plus 1 is less than 0 if you assume that x minus 1 is less than 0. So all we're doing is we're going to multiply this across. So times x minus 1. And this piecewise function will determine whether this right here is going to be greater than or less than. So this is defined over here in this piecewise function. So you can say this way, that x is greater than -1 if x is greater than 1, and that x is less than -1 if x is less than 1. So if you want to make sense of this, that means that in the event that x is greater than -1, it has to be greater than 1. So this really, since you're saying that it has to fulfill both of these, it has to be actually greater than 1, because any value that's not greater than 1 will not fulfill this value right here. So it's saying that x is greater than 1, right? And on this one, it's saying for all values such that x is less than 1, it must also be less than -1. So to fulfill both of these, you have to pick a value of x such that x is less than -1. So that means x is less than -1. So this right here is where this function is going to be defined, which can be put on this range. So -infinity to -1 and 1 to positive infinity. That means any value between -1 and 1 will not be defined. So therefore, x, or the absolute value of x, must be greater than 1. That's the same as this right here. So that's how you're going to solve number 11, and that's what you'll see in the back of the book.